The great engine of our planet's climate is not fixed. It only appears that way from our human perspective, a system so vast and seemingly permanent that we assume its stability. This engine is the global network of ocean currents, a silent planetary-scale conveyor belt of water, heat, and life. For millennia, it has governed the rhythm of seasons, the location of deserts and rainforests, and the distribution of life in the sea. The changes to this system are typically measured on geological timescales, unfolding over centuries or even millennia. But the scenario we explore is different. We are not contemplating a change unfolding over 1,000 years. Instead, we are compressing that geological process into the span of a few short decades. The initial signs would be almost imperceptible to the average person, easily mistaken for natural variability. These early, subtle changes are merely the first dominoes to fall. As the system adjusts, the impacts would grow in scale and significance. The world would not end. Human civilization would continue to function, but it would be forced to operate on a very different planet. To understand the impact of a slowdown, we must first understand the system itself. The Earth's oceans are not a static body of water. They are in constant, organized motion. At the surface, the most visible driver is the wind. Persistent winds, Earth's rotation, and uneven solar heating push the ocean's surface, creating vast circulating currents, gyres. Examples: Gulf Stream, Kuroshio. But that's only half the story. Beneath those surface currents lies the thermohaline circulation. Thermo, of course, temperature, haline, salinity. It's driven by density, not wind. Cold, salty water is denser. Warm, fresher water is lighter. It begins in critical spots, especially the North Atlantic. Warm, salty water carried north by the Gulf Stream releases heat, helping keep northern Europe mild. As water cools and sea ice forms, it gets saltier, denser, and sinks. From the deep North Atlantic, cold, dense water flows south across deep ocean basins for centuries. In places, upwelling brings nutrient-rich deep water back to the surface. Upwelling fuels marine life, which feed phytoplankton, the base of the food web. Scientists do not guess about the state of this global system. They measure it constantly using a sophisticated array of instruments. Satellites orbiting the Earth provide a continuous, planet-wide view of sea surface temperatures, revealing the pathways of warm and cold currents. To measure what is happening beneath the surface, researchers rely on a global fleet of autonomous robotic floats, part of the Argo program. Scientists also use moored instrument arrays, such as the Rapid Array stretching across the Atlantic, giving us a direct reading of the conveyor belt's strength. The concept of a major shift in ocean circulation is not purely theoretical. The Earth's history contains clear evidence of such events. The most famous is the Younger Dryas. After warming at the end of the last ice age, northern hemisphere temperatures suddenly plummeted. The leading hypothesis is a catastrophic failure of the Atlantic circulation, caused by a massive influx of fresh water from melting ice sheets that shut down the sinking process. The takeaway: the ocean circulation system has tipping points. It can absorb some change, but once a threshold is crossed, it can reorganize into a new state very quickly. The first and most immediate consequence of a 30% slowdown would be a noticeable, persistent cooling across northern and western Europe. 30% less flow equals 30% less heat transport. Winters in London, Paris, and Oslo would become colder, longer, and snowier. Summers would be cooler and shorter. Agriculture would suffer. Shorter growing seasons and an increased risk of crop failure from frost would become common. This temperature contrast changes the jet stream's behavior. Storm tracks across the North Atlantic can be steered onto different paths. This could also push the tropical rain belt southward, cutting seasonal rainfall in West Africa and threatening food and water security for millions. A more subtle crisis would be unfolding beneath the surface. A 30% slowdown would mean a corresponding reduction in the strength of the nutrient pump. From space, satellites that once monitored vibrant plankton blooms would now see vast, empty patches of deep blue ocean. This would be a rapid collapse of primary productivity. The very foundation of the marine ecosystem would be pulled out from under it. As phytoplankton disappear, zooplankton populations would crash, leading to starvation for small fish. Within a few seasons, fishing fleets would return to port with empty nets, their traditional fishing grounds having become barren underwater deserts. Coral reefs, already under stress, would face a new threat. A slowdown in currents would lead to stagnant warming water, increasing the frequency of mass bleaching events. The ecological crisis in the fisheries would translate directly into an economic shockwave. For fishing villages in Senegal or Scotland, it's an existential threat. Many younger people would be forced to leave their ancestral homes and migrate to cities for work, creating a new class of economic migrants. The scarcity of key species like anchovy, a primary component of fish meal, would cause its price to skyrocket. This would drive up the cost of producing farmed salmon, shrimp, even chicken and pork. The insurance industry would also react. With fisheries collapsing and weather becoming more volatile, premiums for fishing fleets, coastal infrastructure, and cargo shipping would rise sharply. Disputes over fishing rights would intensify as fish stocks migrate across international borders, potentially leading to diplomatic conflicts over what were once stable shared resources. The global shipping industry has spent centuries optimizing routes based on predictable currents. A 30% slowdown would be like closing a lane on a major highway. The boost from these currents would diminish, forcing ships to burn more fuel and take longer to complete journeys, adding another layer of global inflation. Changes in coastal currents could alter sediment transport, causing accelerated silting in some channels. Major ports could find their entrances becoming shallower, requiring costly dredging. The logistics industry would be forced into a costly, complex re-optimization. The just-in-time global supply chain would be thrown into flux. Over several decades, the initial regional shifts would coalesce into a widespread reorganization of global weather patterns. Stuck weather patterns would become the new norm. This could cause extended periods of drought in some agricultural heartlands, like the American Midwest, and persistent, flooding rains in others. The southward shift of the tropical rain belt would become a global phenomenon, redrawing the world's map of water scarcity and abundance. The character of extreme weather would also change. Accumulated heat elsewhere could fuel more intense cyclones in the Pacific and Indian Oceans. The long-term economic consequences would move into a phase of structural transformation. The initial rerouting of shipping lanes solidifies into a permanent redrawing of global trade arteries. This would necessitate a global relocation of agriculture, with new farming regions emerging in areas previously too cold or too wet. The global diet would also change, with a reduced supply of wild-caught fish being partially replaced by a massive expansion in land-based aquaculture. There would be a clear divide between nations with the capital and technology to adapt and those without. This adaptation gap could become a major source of global instability. After decades of chaotic adjustment, humanity would have largely passed through the crucible of adaptation. Urban planning in coastal zones would look radically different. Crop science would have developed new strains of staple foods resilient to the new temperature and rainfall regimes of their respective regions. The experience would have spurred the development of vastly more sophisticated global monitoring networks, providing real-time health checks on the planet's vital signs. The final outcome would be a civilization that has, by necessity, forged a more cautious and informed relationship with the powerful planetary forces that govern its existence. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.